project is a highly accurate and reliable obstacle detection and avoidance framework for visually and hearing impaired. This is our outline of what we're going to be covering. We're going to go into the team, motivation, system description, all the way to our testing, standards, and ethics.
Hi, my name is Martin Nowak. I'm a computer engineer. I'm head of software design. The things I worked on was the navigation, the mobile app, and some of the image processing.
Hi, my name is Thomas Herbst. I was head of hardware. I dealt mostly with the 3D model and vibration systems.
And I'm Michael Mattis. I'm computer engineering. I was team leader. I did some of the image processing and K-means and 3D printed everything in-house.
There are 1.3 million legally blind people in the United States. And we did our research on the current solutions that they're using to get around. And we found that there were no full rounded, cost-effective solutions. So the things we looked into was the walking white cane. And we found that this didn't really alert the user before they came into contact with the obstruction, and it also didn't take them to their destination. Next was the guide dog, which was highly accurate, but very expensive to maintain for someone with a disability, and it's hard to get a high-paying job to maintain a costly animal. The next was electronic solutions. So we looked into two main solutions, which one was IRA, which is a company that makes smart glasses. The glasses basically has a camera on it, which shows a user on a remote area to see what the person sees, and that person is able to then tell them to turn right, turn left, or find objects that the user is missing. The next was Dr. Ellen and I's research project, which basically was a device wore on their chest around this big. The issue with this was it was too large, and it required a server, which was in the form of a laptop that the user had to wear on their back. But it was highly accurate. So for our societal impact, we aim to change the way people with visual impairments navigate through their day-to-day lives. This device that we made is lightweight, it's small, portable, and it has to work in multiple solutions. So for example, it has to work indoors, outdoors, low light, and bright situations.
So this is our system description. It's a small, independent, lightweight device. The keyword being independent, it doesn't have any external servers. And it can detect obstacles in low light, normal light conditions, and it will allow you to work inside and out. It integrates feedback from computer vision and ultrasonic sensors, because computer vision sometimes is not capable of detecting things like walls or large doors. So to compensate for that, an ultrasonic sensor will detect an impending collision. The feedback is provided both via spoken audio for text-to-speech, as well as vibration motors to give actual feedback on the user's body. And it will provide turn-by-turn navigation based off of the tethered smartphone and GPS coordinates, so that the user can speak the destination that they want to go to, and then allow them to navigate to that destination. This is the overall use case diagram of our system. You have the map server and the tethered phone, which work with the GPS navigation to provide GPS coordinates and instructions. The user can then use GPS navigation, as well as obstacle avoidance, which uses K-means as the primary source of data to cluster points that we determine as obstacles and inform them that there is the obstacle and how to avoid it. And then this is the system description, where you have the camera and ultrasonic inputs going into the obstacle detection, as well as the GPS and compass data going into the GPS navigation. Both are fed by a battery, and these feed into the instruction output, which provides the user the proper action to take with a distinct vibration pattern as well for whatever instruction is being output.
For our related theory, we broke down to the three main image processing techniques that we're using. First being canny. This is a binary output, so all the edges are going to be a white pixel, and all of the other parts of the photo are going to be black. And the reason we chose this was because of the Gaussian filter over different edge detections like solar. Next, we applied ORB, which is corner detection on the image. And basically how that works is it looks for an intensity, whether this is likely to be a corner versus not. We can set that threshold. Next, it does a circular movement. So if it thinks this is a corner, then it moves around in all the directions to see the different pixels in that area. Next, it modifies the version of brief, which is just the descriptor for that point, and that outputs a binary string. Next, we apply K-means, which is an unsupervised learning model, and basically how this works is it assigns points to the image, and then it calculates the distance between our orb points and that cluster. This process is then repeated to minimize the distance so we can make our cluster very tight.
So then some other related theory that we have is for the ultrasonic distance sensor. So basically the way that calculates the distance is it uses ultrasonic frequencies, it sends them out, and then it measures the time that it takes to get them back. And then for the GPS navigation, to actually locate and provide the coordinates, it uses a pseudo range from 4 different satellites. And then this is the Pythagorean theorem that relates all of them. And you get a system of equation that you can solve for the 4 unknowns, which are the receiver clock bias and then the X, Y, and Z.
For our hardware, we chose the Raspberry Pi 3 Plus to be the main computing force behind the project. We chose this because it was a low cost compared to the high power output and the good relative size. We used a Pi camera. This allowed for an IR filter, so it allows for good light and less than optimal light conditions. And the good thing about the camera is that it can connect to the board via ribbon cable right to the processor. The distance sensor, like mentioned, it uses time to calculate the signal emitting and coming back from an object to give us the exact distance. The compass was used in the navigation part of the project. It told us what direction the user was facing so it can give an accurate first direction. The enclosure was modeled using AutoCAD and printed using a 3D printer. There's haptic feedback in the harness system that it tells the user an incoming turn, an incoming obstacle, and also gives patterns that give certain commands like Wi-Fi disconnected and you arrive at destination. The battery, it was important to have a 5-volt output. The amperage was something of interest because if the amperage dipped too low, then the power would shut off. So we needed a suitable 2.5 amp output in the battery. The mounting harness, it is comfortable to wear. It evenly distributes weight, and it can be adjusted depending on the size of the user.
So this was our software for the actual computer vision. We started off by taking an image and converting it to grayscale. From there, we then used Canny to detect all of the edges and fed the Canny image into our orb algorithm, which then marked all of the orb points. We then removed the Canny as that was unnecessary information at that point. And unfortunately, since it's bright here, you can actually see there are k-means clusters, which would have been red circles that are overlaid near the clusters of points which mark an object. And this one would have been just the k-means centers themselves. We strip away the orb because, again, it's unnecessary at that point. And then using those k-means centers, we split the image frame into multiple segments, with these bottom 3 being the impending collision zone for the user. The center is directly in front, and then left and right. And if there are centers in any of those points based off of their pixel location, we can then inform the user there's an obstacle to your right, left, or center, and then provide the proper navigation instructions to avoid said obstacle.
For the second part of our software design, we developed a mobile app which runs on Android. And the point of this was to communicate the GPS coordinates from the user's phone to the Raspberry Pi. How it works is the user presses the button on the top of the device, which then triggers an interrupt. That interrupt allows the user to record their voice. Once the voice is recorded, it sends to Google's API to get the text of what they said. We're able to strip out keywords like take me to and actually get the address. From the address, we can combine the address and the user's GPS points to send to Bing Maps. Bing Maps will then in turn send us a list of directions. And from that direction, we can calculate the distance between the user's current point and the point of the turn. If that point is within 20 feet, we will then alert the user via text-to-speech or vibration that they have an upcoming turn.
These are 2 of my unit tests for the hardware itself. First, we tested the temperature inside the enclosure. It was important with such a small device that the heat didn't damage the electronics. And we found that the hottest parts were the back of the camera and the processor itself, but it wasn't nearly hot enough to cause any lasting damage. The other test was for the accuracy of the ultrasonic sensor. So we just use a tape measure from a wall, and we found it was highly accurate to within centimeters, a few centimeters of the actual distance.
And then the other unit testing that we had to do was for the computer vision components, as well as the navigation. This one you can see that for the navigation, we were able to get the turn to be displayed to the user within sometimes even just 1 foot at max 5. We expected up to 25 to give reasonable warning. And then we also tested the computer vision-based detection, which was mostly accurate. We did have a couple of false positives due to reflections on highly polished floors and surfaces, as well as one false negative when we had a dynamic object that was moving too fast. And overall, when we tested for specific scenarios, if there was a left, center, right obstacle, or even an obstacle blocking their entire path, we were able to successfully say that's what happened.
So for our integration testing, we ran a script that outputted all of our different vibration patterns to see if the user was able to distinguish between a navigation left versus an obstruction left. We also have scripts that run the different outputs. For example, if you disconnect from Wi-Fi or you disconnect from Bluetooth, the user has to know that, and they have to be able to distinguish from the different feedback from the vibration. The next, for our integration, we added all the components from the navigation and avoidance. We tested them individually first, and then we combined them, and we found that they both work together without any interference. For our acceptance test, we concluded that we set out and completed everything that we wanted to do. The device is user-friendly for those who are visually impaired. There is no screen that the user has to see. The buttons are very easy to find. The vibration is a good feedback for someone who uses hearing as their primary sense. The ultrasonic works within a reasonable distance. The system is lightweight and accurate, and most importantly, portable for those with disabilities.
We went through a number of iterations to get the final product we have today. First, we had too many gamings and OR points, and that would show us an object, but we really couldn't distinguish between multiple objects. When we turned the number down a little bit, we could clearly see defined objects. For the model itself, we went through different cameras, so we had to adjust for that on the model. The first camera worked very poorly in the dark situations, so the new IR filter really helped that. Our harness system, there's clips on the side of the box, and we use parachute clips, and it's very adjustable for any size person.
So for our project completion and future work, me personally and Tom, I think Martin already had some background, we learned a lot about Python as a programming language, and he also showed us Visual Studio Code, which is a really beneficial IDE for programming in Python, as well as several other languages. And we strengthened our background. I already had one in 3D printing, but not too much in 3D modeling. So Tom really helped me with that. And then the only thing that we still have to do is, like the first group that presented, finding an adequate battery remains to be accomplished. For running computer vision, the overall battery that we were using at first, it was sufficient to provide it, but the charging circuit that would boost to the 5 volts wasn't capable of providing enough current, and it would eventually shut down. And we will, in the future, refine it with a custom microcontroller because the Raspberry Pi isn't really a highly professional device, and also a custom PCB to connect to GPIO. We'll also use custom injection molding and tooling to build the enclosure and harness system. And one other big thing that we learned was that with CANI, different maximums have a very large impact on how well our device detects objects. So we have it currently tuned that it works well in low light and normal light conditions, but under very specific situations, such as very, very, very rough roads, I have gravel roads up by me, we tested it on that, it will sometimes see those as obstacles when they're not, and that could be compensated by using a higher max threshold. And you can also improve night vision even further by lowering the maximum threshold, which we could do with using like a photocell. You could use that to the GPIO pin and set that, if it sees that it's dark, to then trigger a higher sensitivity canning. Give it a second. Don't click it, just wait for it to work.
So this is our demonstration vibration video. This is just to give you an up-close personal shot of the hardware, the outside. We removed the Raspberry Pi so you can see the layout of the internals. So we have the distance sensor on top, then the camera, and then the compass in the bottom. The vibration controllers, they come out to the sides and one's in the center. This is a demo of the obstacle detection and avoidance. As you can see, there's something on the left and it's telling the user to go right, and that's in the console output there on the bottom. Now we're coming up on more chairs, and it's telling us to go left. And then once we pass them, then it's telling us to go straight. There's one last test here, and it's telling us to go right. This is how we pair our device with Wi-Fi. That's done through the mobile app. After it pairs through Bluetooth, you're able to set the SSID and the Wi-Fi password, and that's sent to a JSON object to the Raspberry Pi, and then it will give the user a message whether it was successful in connecting to Wi-Fi or unsuccessful. You can see here that we connected. So for our navigation, we gave it the address of our school.
Take me to 4513 College Parkway, Bronx, New York.
After that, it's going to take some time to process the audio, and then more time to send you big maps over the internet. And once that comes back, you can see the list of directions with the compass turns. So when we come to this intersection here, it's going to alert us before we get to the street that it needs to turn right. So just for demonstration purposes, we put the output on the phone so you can see it, but the real output is through audio and through the vibration.
When we did the project, it was very important to keep costs as low as possible. Because, like we said before, the other solutions were expensive and there was a barrier to entry. As you can see, the most expensive part was the Raspberry Pi. It was also the most important part, so it was necessary. There's a number of standards we had to adhere to, such as the Bluetooth and Wi-Fi between the phone and the device itself. There's also battery standards, mainly for mobile devices and the safety with them. More standards for the wearable devices. It's important to the location of the device on the user. It's right on the chest, so safety is definitely a major concern. Ethics. Since this is for people with disabilities and visually impaired, it's important to be realistic and honest because the truth is they're relying on the product to safely guide them through the world. And we want to be sure that our team's realistic, that they don't leave us when we're flying. The way we found ethics, like between ourselves, the checks and balances, for instance, like it has to be, you can't say it's 100% perfect when the truth is it's not, and it might get someone hurt.
So overall, we designed an independent device that allows for the navigation of and obstacle avoidance of visually impaired people. It works inside and out. It integrates multiple sensors to allow for detecting obstacles that one alone could not. And it works in both well-lit and low-light conditions. It's more economically accessible than most of the solutions that are out there today. And it's lightweight and comfortable enough to be worn for a long excursion and allow them to be able to get where they're going.
Any questions?
Got two questions. First of all, great project. I like it. Never seen anything like this. First is, do you envision this, like obviously this is still a prototype, but do you envision this product to be a standalone product or more like a supplement to like having the things?
We want it to be standalone once it's well enough developed. I know I was talking to Jonathan before. He actually worked for IRA before we actually knew that he did. And he was saying that they're even looking to try to integrate computer vision and devices like this into their devices to eliminate the need for an additional operator. So if you can make it standalone where you have this device providing all of the obstacle avoidance, that would be the ideal situation.
And the second question is, I understand this is an obstacle detection, but is there, how should I say it, is there an opposite? Is there a way to detect the lack of obstacles? So let's say if you're coming up on a cliff, for example, it's not, is it going to detect that there's nothing in front of you?
In most cases, like we actually tested this even with like potholes, for example. When we were looking at Dr. Omanai's project, it wouldn't always necessarily catch them because Orb is looking for corners, not edges. But with the Canny, even down to like a 1-inch lip from a pothole, it was actually capable of marking that with the Canny edge and then providing an Orb point on top of that, which would then be clustered and allow it to be marked as an obstacle and essentially tell you to avoid it.
Awesome, thank you.
Any others? Thank you.
Most of the devices not that great when it comes to dynamic detection. So what was the solution in order, because I see in your video that there's some dynamic or let's say the sudden appear object. How do you overcome this issue?
So with that, we had the lower maximum thresholds for Canny, so it would actually look for softer edges, and by doing that, it would detect as things were moving. Like I said, it still did miss one very fast-moving object, which we kind of expected with Canny, but by lowering the maximum threshold, it looked for softer lines and was able to actually detect that, mark it, and then Orb could come in and take care of it.